Hi, Alexa. Oh,
He dies in that
Nathan's
one.
out too.
He dies in every movie.
It's a great
Yeah,
movie.
name a movie.
National Treasure, that's it.
There's gonna be a National Treasure 3, and he will in fact die. I don't know. Probably.
Yeah, they will. I know.
It's got Nick Cage. There probably will be another one.
He eventually has to die.
Yeah, you can't just leave a series without Nick Cage dying. It's impossible.
Alright.
So whoever's watching this video now has like a 2-minute discussion about Nick Cage recorded on here. So, thanks, Colin.
Did you feel special?
That's for me.
Oh, in which case, might as well just turn it off. Oh, where's the microphone?
Okay.
What did you say? We had to mess with names as much as possible.
Oh no. Alright, so.
Just block the camera. Just don't even. So this is he has the sound of what we're learning about, but no.
No, Alexa's not here too. And she matters.
Nate
Nate's
won't do that. He won't do that.
I was like, he's not gonna watch it.
Go to the second game.
Alright, so.
We don't care
Oh
about
my
Nate.
god. If you remember on Friday, we did that first derivative test, so that's what you guys missed, and I'm sorry. You might actually be able to catch the drift of it, or the gist of it today.
The drift of it.
The drift, the gist, whatever. So we talked about before that if the derivative of something is positive, then the function itself is increasing. And if the derivative of something is negative, then the function itself is decreasing. And when that change happens from increasing to decreasing, we have a max. And when the change happens from decreasing to increasing, we have a min. Whether it was a smooth thing or whether it's a cuspy thing, it would still have the same characteristics as far as when it changes from increasing to decreasing. I'm always going to have a max and vice versa. There's another test that comes with the second derivative. And the second derivative tells us a lot about the concavity of a function. So it's not quite as detailed as the first derivative test. So let's just look at something like the cubic function. Because the cubic function changes concavity. We don't really talk about concavity much in like pre-cal. But it's kind of important because a function can be both increasing and concave up or increasing and concave down. And this is an example of that. Concave up, in case you don't know, looks like a cup. So it's when something is like that. Concave down looks like a frown. So it's basically talking about like what that curve looks like, whether it's a smile or a cup or whether it's down like a frown. So where does the concavity of x to the third change? At zero. Okay, at x equals 0, the concavity changes. So it's clearly a frown until here, and then, oh, it's a smile or a cup after that. So there's something that is specifically important that relates to the second derivative. So let's see, how should we say this? Let's look at it this way first. If I look at this and I take the first derivative, I would get 3x squared. If I was thinking about critical values, I would set this equal to 0, and where would my critical value be? At x equals 0. Really easy to find. It didn't come from the first derivative being undefined, so I know it's not a corner or cusp. But because the first derivative is 0, it's potentially a max or a min. Well, this is that third possibility. So on Friday we had like, if the first derivative is 0 or undefined, it could be a max, it could be a min, and then the third one was it could be neither of those things. This is one of the cases where it's neither of those things. It's not a max. It's not a min. It's neither. Nor is it a point that's undefined. It's not like when I put 0 into the original function, it's an undefined spot. So it's a good example to look at anyway, just to see that when I have a critical value, it doesn't necessarily mean anything. It could just be hanging out. It does mean that the tangent line does equal 0 here, so this is actually really flat. I don't have it drawn really super well there, but oh well. So let's keep going further and look at the second derivative. The second derivative is 6x. I'm going to do the same thing with the second derivative that I did with the first, where I'm going to set it equal to 0, and if it had a denominator, I would set that equal to 0 also. Little disclaimer, those are not critical values. The only critical values are the ones that come from the first derivative being 0 and undefined. The second derivative equaling 0 undefined, they don't have any. They're just like points. I don't know. So there is no name for this. If a test ever asks you for the critical value, it's from the first derivative only, not the second. So anyway, I'll still go forward though. I take the second derivative equal to 0, and I get x equals to 0. I'm still going to make a number line just like I did with the first derivative test, except this time I'm going to label the number line with second derivative and the regular function. So tell me what's true. When x is less than 0, what's always true about the second derivative? It's negative. Okay? When I pick a number in this graph that's less than 0, it's always going to make the second derivative negative. And if I pick a number bigger than 0 and plug it in, it's always going to make the second derivative positive. Well then, how does that relate to the graph? If the second derivative is negative, well, we already said when x is less than 0, what's the deal with this graph as far as concavity goes?
Down.
It's always concave down. So if the second derivative is negative, the function is going to be concave down. And conversely, if the second derivative is positive, the function is going to be concave up.
This for all functions? Or
For
just
all functions. So for all functions, 0 is not going to be the cutoff, but when the second derivative is negative, function will be concave down. Second derivative is positive, function will be concave up. Always.
So you can have more than just a 0. You can have a bunch of points there too.
Yep. Yeah.
If your second derivative is just equals 6, then you know.
Then it would be, so if my second derivative were 6, what is this derivative then always?
It's just almost
positive.
The derivative, second derivative is a line, but it's always positive. It's a constant, it's always positive, so that means my graph would be always concave up. So for example, what if I had the graph y equals x squared? The first derivative is y equals 2x, and the second derivative is y double prime equals 2. So the graph y equals x squared, the second derivative is always positive, so it's always concave up. The first derivative is not, though, always positive. Where's the critical value there? At 0, right? And so the left of 0, anything less than 0 would give me a negative, which means I'm decreasing. And anything to the right of 0 would give me a positive, which means I'm increasing, and I've got that min in between them. Okay. Putting it all together. Let's do something kind of simple, and look at the derivatives, and give us, together, and let's give ourselves a sketch of what it's going to look like. And then it gets kind of crazy. Because the point is not to graph x to the third, you already know how to graph that. The point is to graph crazy stuff that you don't know how to graph otherwise.
Like trig.
You know, we don't do this a lot with trig. Trig gets like a little bit crazy. Let's look at,
It's just awful.
oh, this one's really,
You're scared of the church.
Right, Dan?
What?
Dan,
Scared of the church.
Tell me all
if you're scared, you go to church.
It's all for you.
yeah, the clock's all like crazy. I'm just gonna grab my,
It's 12:43.
2x to the 4.
Time's flying now.
right?
Glad you're having fun.
Okay, a problem might ask you, find all the critical values, or find where the graph is increasing, or decreasing, or find where the graph is concave up or down, or, oh, I didn't tell you.
There's more.
No, just a vocab word. When the concavity changes from concave up to
Point of
down or vice
inflection.
versa, it's called a point of inflection. We didn't, do you know that?
He does.
A point of inflection is when, whoa, concavity changes.
My handwriting.
It's like my cursive on SAT. What?
and we'll talk more about like how to justify your answers, because it's a big deal on the AP test. How do you justify, how do you explain your answer? So that they say, where's the point of inflection and why? You could say the point of inflection in the last one was at x equals 0 because the concavity changed from up to down, or down to up, or whatever. So when it changes in either direction, it's a point of inflection, whereas with the first derivative, if it changes from plus to minus, it's a max, and minus to plus, it's a min. So it's a little more specific. Point of inflection is just more general. Okay, we're going to find the mins if there are, maxes if there are, points of inflection, and we're going to graph it. All with our handy-dandy tool called calculus.
I thought she was going to say calculator for a second.
Oh,
I got
no.
both.
Anything you need.
What class?
He's having a fun time. Let him
I really hope Nate's using it.
You just enjoy your moment.
I'm just hoping Nate's using it.
do. Nate wants to.
He's not
No way
going
Nate
to.
watches this.
Yeah.
No. He
No
barely
way.
watches during class.
What if he
What
doesn't
is
watch
this?
this, guys?
No, it's not.
Alexa.
Let's all make fun of him so he
Brooks,
feels
talk
real
about
awkward.
art.
Right.
Watches it.
Brooks,
Never
just,
know.
just walk in from, just put your face.
I'm
in
gonna
the
raise this
camera.
one.
We can
Okay.
send that video to
Step
you.
number 1, take a derivative.
To his mailbox.
Play on his TV when he walks in tonight.
She doesn't have power.
Someone still doesn't have power?
Yeah. Alexa's still out.
Oh.
Then why are we filming?
That's terrible. Okay, so this becomes pretty systematic. First step, take a derivative, set the derivative equal to 0, blah, 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 or make it undefined if you need to, if you have a denominator, and find your critical values. So in this case, be sure you don't divide everything through by x, that would be silly. So I'll factor out, say, an 8x, and I'll be left with x squared minus 1. So I have critical values at x equals 0, positive 1, and negative 1.
Just wave that kid.
Or just like,
Just
slim.
start knocking.
Press your faces on that window.
Yo, Dan, good knock on the
Turn
window.
over.
Dan, you knock on the window.
sorry you're
distracting
distracting
class.
Go knock on the window, but you gotta hide
You're
afterwards.
being
No, do it. Do it. Go knock on the window, but you gotta hide. You gotta hide. Alright, we're still having class. Do it, right now.
Knock on the window.
Knock on the window, Brooks.
Why do you think people don't trust Republicans, bro?
Kids are creeping
Because they creep us out. I'm just kidding.
Oh, we're pumped.
Okay.
You gotta
I'm done.
All
Alright.
Go. You gotta hide them. You gotta hide. You gotta wink at them. That's just creepy.
Just make an angry face and like pull down the blind.
Okay,
That's
so
what I was
it's
saying.
ideal.
Yeah, but slowly.
The first derivative first. Every year.
Like level 5.
Really?
Oh my god.
No!
Alexa, I'm sorry.
Yeah, then
She wanna
they
be
know.
Fast forward.
Oh,
We're good.
quality cameraman over here.
We're good.
What kid?
He's challenging you.
They probably think we're level 5 because we're just like laughing.
That's what I just said.
Oh, I thought you meant
No, I wasn't saying
they were
girls, I
level
said
5.
we're level
Brooks.
5.
Messed up, dude.
That kid's challenging you.
That kid's scared for his life.
Yeah, that kid just did like
That
parkour.
kid has a lollipop.
Okay, anyway.
So,
Every year, I feel like I make it really clear how your explanation should look, and every year people screw it up. So, this is important when you're trying to describe what your maxes and where your maxes and mins are.
Sean,
So
where's
make
your
this
food?
number line and label part of it y. Stop. And label part of it just y. And now we're going to go through each little partition, plug a point from that interval into the derivative, and decide if it's positive or negative. So you don't have to worry about what the number is, you just need to know, is it positive or is it negative? So like when you're plugging in, you can plug back into the derivative, or even maybe the reduced version. I like plugging it in here, because then all I need to know is like, for example, if I plug in a -2, a -2 here, I don't care that it gives me -16, I just know that it's negative. Times a what? If I plug -2 in here,
Positive.
a positive. So a negative times a positive is negative, and that's what I need to know. So don't spend all day like trying to get the exact number, just figure out if it's positive or negative. Especially here when I get into fractions. So -1/2, I got a negative here, but then here,
It's gonna be negative.
a negative again, so when I multiply them I have a positive. Between 0 and 1, I have a positive and a negative, so I got, right? A minus. And then bigger than 1, positive. It does not always oscillate like that, minus, plus, minus, plus. You really do need to check all the intervals to be sure. So when I have this, the big information that I need to draw from this is, when the derivative is negative, y is decreasing. When the derivative is positive, y is increasing. And yes, you have to write that. But what's great is that there'll be plenty of an explanation on any open-ended problem
If you remember all this.
about why something is increasing or decreasing or has a max or a min or whatever. And then I go through and I just label what was my max and what was my min, or plural. So if I go from decreasing to increasing, what's happening here? It's a min. Decreasing to increasing. Think, just like, do a little picture in your head. Going down to going up. It's got to be a min in between them. Increasing to decreasing, max. Decreasing, increasing, min. Do you understand where I'm getting all this information?
Yep.
Okay. Also, before I go any further, I just write down where these all are. My min is at -1 comma, whatever. Where do you put those x's into, the original or the derivative? The original. If you put them into the derivative, you should get 0 for all of it, because that's how you found them in the first place. So put them into the original, and now you actually do have to do the math. So like 2, -2,
The calculator.
-1. This would be a no calculator problem,
Oh.
obviously. Otherwise, you could just graph it on the calculator and get all these answers.
-1.
0, 1, and 1 should also be -1. Questions so far where I got that stuff? Alright, second derivative. You can tell that like you can only get like a couple of these on a test because they take forever. So second derivative, go to either first derivative that you want and take the derivative of that. So I would not go do product, well that makes no sense. I'm going to go back to this one and take the derivative from there. So I have 24x squared minus 8. 24.
What does it
That's a
mean?
number, all right.
Here's where you're going to hate your life. So x
Uh-huh.
squared is
Fair
8
one.
24ths, and I have to take the square root of that.
That's just
So it's that 1/3, positive or negative square root of 1/3.
Yes.
So I'm going to make another number line. I'll put negative square root of 1/3 and positive square root of 1/3.
so many number lines.
Yep. And now I'm labeling it with the second derivative because I want to know what's going on with the concavity. It's so exciting.
So plug in 0, -1.
So, right,
and
so it's
1.
pretty easy to plug these numbers in, even though the actual points are really annoying. So if I plug in 0 into the second derivative, I get a negative. If I plug in something bigger than the square root of 1/3, like 1, I get something positive. And if I plug in something less, like -1, I also get positive. So my graph is concave up, concave down, concave up. That would be a completely labeled, like, second derivative test. One other little thing. Oh, so we already said this, I guess, but here's your point of inflection. I'm going to label it. And usually, like on the AP test, these would not be so hard to find. It'd be more like the first derivative turned out to be. They probably won't make you find the y value that goes with them. Okay, I'm not gonna plug them back in, that's ridiculous. Even though it's actually to the fourth, it probably wouldn't be that bad, but still. Gross. Okay, so when they ask you where's your mins, there they are, where's your max, there it is, where's your points of inflection, there are these. Let's graph it. So I just go put down all these points. I've got a min at -1, -1. I've got a max at 0, 1. Another min at 1, -1. And what's important is just to know basically where these points of inflection are. So they are, as an x value, between 0 and -1, right? This point of inflection is somewhere in here, and this one is somewhere in here. So you may just want to watch it get graphed and then write it down. I know that to the left of -1, the graph is decreasing. I'm getting to a min here, and it should be concave up, so it should look like a cup. So from here to here, it should be coming down like this, but looking like a cup. So something like this. From -1 to 0, I know that I should be increasing now. I'm coming up to a max. And somewhere in between here, my concavity changed. I don't know what the y value is because I don't feel like finding it, but I know that somehow it's like concave up, and then I'm changing the concave down. So somewhere in here is a point of inflection. And if I wasn't feeling so lazy, we should probably find the y value of it, but they're never going to make you do that much math. I won't put it on 0, 0, so you know it's not there. But I won't put it at 0. As I continue from 0 to 1, I'm now, if I look back at my thingy, from 0 to 1 I'm decreasing. I'm headed towards my min. And I'm concave down until I get to this stupid point of inflection again. So I'm coming down, turning from a frown into a smile. And I have another point of inflection somewhere around there. And then bigger than 1, I'm increasing now, and I'm still concave up. So it looks like that.
Will it always be symmetrical?
No, what makes it symmetrical? How do you know?
It's four.
It's even.
It's even. Remember that even odd stuff?
Ooh.
So it doesn't come up that often, but if you do see all squareds in your thing, you could be like, oh, I know this is even, so it's just a little help. Yeah. It's awesome, right? Should we do one more? What time is it?
Oh, I have a watch. 12:57.
Oh, we do have time.
Oh, that clock is.
It's 12:56. I think. So I think it's
You
been
just
used.
change your watch to do the same time.
Yeah, I changed it 4 hours and 25 minutes back.
Yeah,
Just for thrill.
that's how it works.
Just to mess with people.
What if you changed an hour once a month, so then, like, within 12 months, like in a year, will be
That'd be
up
so
during
messed
the
up.
night and
I think there's a reason they do that.
You tried it. You tried it.
You tried out first. And
Was it you guys who told me? Was it you guys who told me that if you actually take a nap, what is it, a 20-minute nap every 4 hours?
I know about that
I
though.
didn't say that,
I
but
didn't.
I read that somewhere.
Yeah,
What?
I really wanted to try it.
You could be
What is it?
Superman. You
You
take, because you only need like 2 hours of sleep. If you take a nap, a 20-minute nap every 4 hours, that's like all the sleep you need. But you have to do it every 4 hours, or else it completely destroys your sleep schedule and you feel like awful.
Yeah.
Just 20
Needs
minutes?
to be
20
reconciled.
minutes.
I'm gonna try that
You
for like
might
a week in the
actually-
summer.
Seriously, so like at 6 a.m.,
Summer thing though.
You take a 20-minute nap and
and
then
then it,
So much more.
4 hours later would be 10.
20-minute nap.
That'd be
At
more
2.
trouble.
20-minute nap.
Oh.
But like
At
you can't
6.
miss the naps though, like
Right.
because if you do, you just throw it all off.
To be able to get down, like, you have to, like, get in pajamas.
Just like brush your teeth.
Oh.
Take your contact lenses out, brush your teeth, sing a song, hold your
You'd
binky.
be so clean.
Just kidding. Yeah,
You
right.
Like take a shower every time you wake up.
Oh, I had to have their sleep.
I've been doing my hair a lot.
That's
Okay.
a warm mill.
All right, so this is more reasonable of a problem that you're going to see. It's going to be
Looks
something
more
like,
reasonable.
it'll be like kind of gross.
So-
It's not actually as complicated as it looks. You really don't know what that's going to look like at all.
I can see in the future.
It's probably straight on, isn't it?
No, it's not.
Well, I guess
How
it's
would
a
that
complicated
ever
thing.
be? Straight line.
So we go take a derivative. Now before we even start, it's actually a good idea to think like, Is there any spot where this is undefined?
No.
You're, like, everything's to the 2/3 or 1/3, so like, you're cube rooting everything, and cube rooting's fine, so I don't have to worry about like negatives under there. There's no denominator, so there's really no undefined points. So that's kind of a good thing just to know. If you had an x in the denominator, you're gonna have an asymptote there, probably. So it's like, kind of good for that to stand out for you. So, derivative, what do we have to do to take the derivative?
Product rule.
Product rule.
Yeah.
So the first times the derivative of the second
Which is ugly. Yeah, it looks really a lot better.
plus the second times the derivative of the first. Oh yeah, easy peasy.
No big deal, right?
That's awful.
Can you handle the algebra of this?
Probably
My soul.
not.
Oh, can I stop you for a second? I'm just looking at
Yeah.
mine because I already done this.
Oh, good.
Right, we shouldn't use product rule.
What?
That's way too gross. I'm looking at it now.
Are we
There's
gonna
no way to
distribute those
distribute that.
things?
Yeah, distribute it first.
I'm glad I already wrote it down.
So am I.
We're just gonna write JK. Do this.
Yeah, why would you want to take the derivative? Like when I started going through them, that's too much. And that should come in your head. If it's too much like that, it's probably, there's probably an easier way. So y itself is 3x to the 2/3 minus 2x to the what? When you do x to the 2/3 times x to the 1/3, what do you do to the exponents?
2 9.
Add 'em.
Add
How
them.
you know?
So it's just
X.
1x.
Minus 2.
Mhm.
That's awesome.
So when you distribute that, that's how that distributes, because So now my first derivative, so much easier, is going to be 2x to the negative 1/3 minus 2. Wow, it's a lot easier. Everybody understand that?
Yes, ma'am.
Okay. So we have to find the critical values. Now here's where I say, you got to put x to the 1/3, next negative 1/3 in the bottom, and make a common denominator out of this. So I really think it's important to do that and go common denominator of x to the 1/3, so we're going to have 2 minus 2x to the 1/3. Everyone see that? I'm taking 2x to the negative 1/3 down, and then making a common denominator of that. Is everyone okay with that? Okay, now I want to find the critical value. Set the top equal to 0, set the bottom equal to 0. I think it's a great idea to have your critical values and kind of keep track which ones came from the top being 0 and which ones came from the bottom being 0. And this is what I was talking about on Friday. When the bottom is 0, that means the derivative was undefined. So it's a corner or a cusp or a vertical tangent line, or maybe the original was undefined. It's not in this case. When the top is 0, it's a smooth max or a smooth min or a smooth horizontal tangent line of some sort. So it's a big deal to kind of know what the differences are. So for this one, what critical values do we get? Bring over the 2, divide by 2, we get 1. And for this one, we get x equals 0. So there's my 2 critical values. We're like 10 minutes. Isn't it weird to like, I don't know, I like to know time. Okay, so I do the same thing. I make a number line. I label it with y prime and y. And I start plugging in. I want to plug into the easiest place. So for me, I would say, I plug into here. When I plug in something, I'll start easier, bigger than 1. If your brain needs it, plug in something that's easy. So if I have x to the 1/3, what's a really easy number to take to the 1/3? What?
9. Actually, just kidding. 8.
8. Close. So 8. So if I pick 8, 8 to the 1/3 is 2, right? 2 over 2 is 1, minus 2, that's a negative. Between 0 and 1, so I have to pick a fraction to check this out, but what fraction should I pick?
1.
1/8. I pick 1/8. The cube root of 1/8 is 1/2. Flip it is 4, minus 2 is positive. This is a good problem. If you feel confused by it later too, go watch the video online and look at just this last part, because this is a really good problem. Pick something negative, like -8. Cube root of -8 is -2. So this is -1, so this is still negative. So y itself is decreasing and increasing and decreasing. So when I go from decreasing to increasing, I have a min. When I go from increasing to decreasing, I have a max. My min happens at 0, comma, go to the original, 0. And my max happens at 1, comma, I put 1 in here, 1. We're okay with that? Okay. Go second derivative. I would take a little bit more time if I didn't think that that was going to remain honest. Second derivative, go take the second derivative from any step that you want. I'm going to go to here, because that's going to be the easiest. So I'll have -2/3 x to the -4/3 minus nothing, because derivative of 2 is 0. Let me ask you a question, just to speed this along and to give you something to pick up on. I know my critical value is 0, but what happens no matter what I plug in for this?
Positive.
I'm going to get a positive number, right? Because x to the 4/3, I'm going to be fourthing it first. Well, x to the 4th, whatever I have is positive, so the whole thing, this is always less than 0.
So it's always negative.
So like, since x is always positive, this whole thing is always negative because of the negative up there. So y is always concave down. I don't have to make a number line for that when I see like, oh, it's always concave down. So if I go try to graph it, at 0, 0 I have a min, at 1, 1 I have a max. It's always concave down, so it always looks frownish, always looks upside down like that. And let's try to piece that together with the decreasing, increasing, decreasing thing. So to the left of 0, I'm decreasing, and I'm concave down, so I gotta look like this. From 0 to 1, I'm increasing, but still concave down. And then after 1, I'm decreasing, and still concave down.
Oh, it's a cusp.
It's a cusp. And
Look
it's
at
kind of
that.
like reaffirmed this one, this critical value of 1 came from the derivative equaling 0, right? At x equals 1, that critical value is from the derivative equaling 0. Perfect. Horizontal tangent line. This critical value at 0 came from the derivative being undefined, corner cusp. That's pretty stinking awesome.